So last time we briefly classified two types of phase transitions, namely the first order or continuous or second order phase transitions. So today we will more rigorously define what I meant by this first order or second order or continuous phase transitions. First of all, the bulk free energy density Fb should be everywhere continuous, and we will talk about that in just a moment. And under such a condition, the first type is the first order phase transition, where we have the jump or discontinuity across the phase boundary for the first derivative of this free energy density with respect to the coupling constant Ki. So it can be one or two or more than one first order derivatives free energy density with respect to the coupling constant, which are discontinuous. And we could see what happens from this plot here, that this is a plot of free energy density at B versus the coupling constant Ki. And as you can see here, we have a level crossing, namely the state 1 marked by red go from this left bottom to this top right. However, this yellow line indicates the second possible states, and which goes the other way. So they have intersection right at this critical point. But this is the first order transition, because if we look at this ground state or the lowest energy state, which is more stable, and we can find that this for K less than critical value, it is the red, which is the state 1, which is the lower in energy, which is the ground state, which we call this phase 1. Above Kc, it is a yellow line, which has a lower energy than this red line. So it is the phase 2. But right at this critical point, there's a kink. It's a sharp edge. It's a kink right at this critical point when we plot this free energy density versus this coupling constant. So that kink does not violate this continuous conditions of the free energy density, but it gives rise to this jump, or this continuous point across the phase boundary, and that jump defines this first order phase transition. Okay, so this is called the level crossing. And this level crossing transition occurs in many phase transitions in nature, in physics. So this is sudden jump, this first order derivative of free energy density with respect to coupling constant would not give as the interesting scaling behavior, power law behaviors near the transition. So it would not lead to this universality class and this interesting power law scaling and so on. So we will not focus on this first order transition this class, but we will focus more on this continuous phase transition, where this first order derivatives free energy density with respect to coupling constant are all continuous across the phase boundary, but in many cases it is a second order derivatives free energy density with respect to coupling constant which shows a jump or a discontinuity, as illustrated in this plot here, that the free energy density versus coupling constant show some kind of a void level crossing. So these two states will never cross each other, even at this critical point. So for K less than critical value, it is the red state 1, which is the ground state, and above critical value is the yellow, or state 2, but this red and yellow actually connect continuously at the transition, and these two curves never cross each other. But you can see that if you take the second derivatives free energy with respect to this coupling constant, you can find these two parabola curves, and one is concave and another is convex. So it gives rise to different positive negative value of this second derivatives free energy with respect to the coupling constant, and therefore there's a jump at a second order derivative level. So sometimes it's called the second order phase transition, or more rigorously we should call this continuous phase transition, because in many cases this jump does not occur, but divergence, singular behaviors may occur when you take the second order derivatives free energy with respect to coupling constant. So not all cases of the continuous phase transition have this jump, the second order derivative, but in some cases it shows a divergent singular behavior. But in all cases, this first order derivative free energy density with respect to coupling constant are all continuous. So we call this continuous phase transitions, to be more precise. So that's the more rigorous definition of the phase transitions. So now let's look at another issue which we talk about, which is thermodynamic limit. And we ask ourselves whether or not the thermodynamic limit really exists in nature, because we know that the volume of the system, any materials in the lab cannot be infinity, right? So it is a finite size system, even though this size is actually very large and it consists of many, many atoms in there, so but it's still a finite size. So in what sense do we mean that we reach the thermodynamic limit, okay, in real material? And this brings us the concept of finite size effect, because all systems have a finite size, and what the system will look like if we consider this systems as a finite size system, and what about the thermodynamic limits at the finite size? Okay, so to that end, we should define a very important concept called correlation length. Okay, so the reason why we need to define this are twofold. Number one, that in real systems, the size of systems never be infinity. Okay, it's always finite in size. Meaning this, even though this number of particles about 10 to the 23rd that many atoms, but still the size of system is actually finite. Meaning it is not infinity, it's less than infinity. And number two is that close to phase transition, this correlation length diverges as the system goes to the critical temperature. Let me remind you what I mean by the little t. This is a relative distance to the critical temperature that we defined earlier at the finite temperature phase transition. So the correlation length diverges in the power law fashion when this temperature is close to the critical temperature. But what is the official definition of the correlation length C? So this correlation length is defined as a length scale R, where this finite size system shows the following property, that if we measure the density of the system and also the fluctuations of the density of the particles in this large but finite size system, they are comparable. So delta average, this observable O, refers to the fluctuations, and this average O refers to the average value of this measurable quantity O. And if the average size, the average value of such a measurable quantity is approximately the same quantity as the fluctuations, namely we cannot distinguish between the actual size of the average of this measurable quantity and the fluctuations of that quantity. If that is the case, then we define the distance or length scale, where these two quantities are comparable to each other, the correlation length. So the correlation length, ideally in the thermodynamic limits, should diverge. However, we know that the thermodynamic limit never been reached. So the thermodynamic limit is never reached in real system. So which means that at the length scale larger than the correlation length, or when the correlation length reaches the length scale of the system, okay, suppose this is my finite size system with a range L, so we know that this L is never reached infinity, but a finite value. So when the correlation length, which tends to diverge near the transition, but for a finite size system, the correlation length never diverges. Okay, so it should reach to the maximum value of the length scale, which is bounded by the system size. Right. So the consequence of this upper bound of the correlation length indicates that there's a little t here, this dimensionless couplings or dimensionless temperature cannot be as low as we want. It means that this little t should have a lower bound. So we will give you some example to illustrate this point, that this is called finite size effect. But nevertheless, over a finite size, we can still see the signatures of a phase transition, but only over this system size. Okay, within the system size that we could see the signature of the phase transition. So let's just analyze this more quantitatively. So suppose that the correlation length as a function of the little t goes like this prefactor C0, which is a correlation length where the system is well away from the critical point, times this little t to some power, which shows some divergent power, say the minus 2/3, and this C0 is a correlation length when the system well away from the critical point. For example, this C0 for a superconductor is about 1,000 angstrom. The maximum system size for, say, typical superconductors may extend over say a centimeter, so which sets this lower bound for this dimensionless temperature, little t minima, and we could calculate this t minima, which is about 10 to the minus, say, 11. So that is the closest temperature to Tc that we can reach. It is really close to this critical temperature because if you plug in this definition of this little t, you can see that this is T minus Tc over Tc. So suppose the critical temperature for a superconductor is about, say, 10 Kelvin or 100 Kelvin for high Tc materials, and that's T minima is 10 to the minus 11, which means that you could go as close to Tc as possible in the lab, and the relative difference between this temperature you can reach to the critical temperature Tc is really, really tiny. But even so, we cannot push this little t any lower than T minima. So little t cannot be smaller than this T minima. But if suppose that experimentally we could manage to lower temperature even below little T minima, what happens? If the little t is actually less than T minima, then this finite size effect will dominate. Okay, in other words, this continuous phase transition or the scaling behavior is going to smear up, and they become not very clearly seen once your temperature is lower than T minima. Okay, because that is where this correlation length reaches the system size, which is a finite value. And you cannot go beyond or larger than the system size for this correlation length, because that is the natural boundary for this length scale. But ideally, we know that this correlation length should diverges in the thermodynamic limit, but in reality, we can never reach that limit because precisely for this reason. But if we probe the system above this T minima and below the correlation length across the system size, then everything should be fine. So we could still see signatures of a phase transition. If we don't touch the boundary of the system size or the lowest temperature T minima corresponding to this finite size, then we could still see the signature of the phase transition. But there's a limitation of this scaling behavior or this power law divergence of this observables near the transition, and that limitation is set by the finite size. And we will come back to this later when we talk about this finite size effect to smear out this transition, and the transition becomes a blurred crossover. So that will be discussed later. Okay? So let's continue. So we just talked about the finite size effect and correlation length, which actually set the boundary of this phenomena of phase transitions. And we cannot avoid the finite size effect. It's just how we could actually manage this finite size effect. And there's another aspect of this theoretical understanding of the phase transition. It is the models. Okay, what kind of theoretical models that we could use to provide us with insights to understand this interesting phenomena. And there are oftentimes in physics two approaches to the model calculations. And the first approach is what we call this realistic models, where try to come up with a very realistic as possible. We know that the real materials are very complicated with many atoms and hundreds and millions of couplings, and therefore to accurately describe such materials we need many parameters. Okay, in the theoretical model, in order to actually fit all this coupling constant and so on. So that's one way, but this approach has serious drawback. And number one is that there are so many coupling constants or parameters in these real materials which we don't know the key ingredients, okay? Because there are so many, and that large amount of parameter space is really difficult for us to really pin down which parameter or coupling constant is the most important one. And so this sounds like an ideal approach which allows us to more realistically capture all these observed experimental features of the real materials, but this is not practical. Seems practical, but in reality this is too good to be true. So, as I mentioned, this is not a very practical choice because we cannot exhaust all coupling constants. We don't know which coupling constants are more important than others. So here comes the second approach, where we try to construct a minimum model, where we try to simplify the model to the simplest possible we can imagine, and yet we can capture the most important features of the experiment. So that is a very clever and a more realistic approach than the first approach. So the first approach seems realistic, but it's not realistic at all. And the second approach sounds very naive, but this is really a more practical approach because, number one, we are able to analyze this minimum model, and number two, and oftentimes from these minimum models, we can extract the key features, and especially when the microscopic physics emerges only very few coupling constants. So this oftentimes shows up in many branches of physics, such as this BCS theory of the superconductors, and also in many examples, as we'll see later, that these observables often showed model-independent features, which we call the universality class. And we know that two very different, seemingly very independent systems, but at the transition, they look exactly the same. And this power law exponent near the transition for these seemingly very different systems have exactly the same value, and this value is independent of the modeling coupling constant. For example, this alpha, beta, gamma, and delta, and so on. So these critical exponents that we introduced earlier, oftentimes they depend not on this coupling constant itself, but just the dimensionality and symmetry. So as simple as that. Well, and then the nature of the couplings. Okay, it doesn't depend on the coupling, the value of the coupling constant, but it depends on the type of the couplings and the dimensionality and symmetry of the model system. And all these nice properties could be actually illustrated and clarified by this randomization group analysis, which we will talk about later part of this course. And under RG, we can throw away all those irrelevant couplings, which we tend to think that they are all very important if we take the first approach. But in fact, there are only just one or two couplings in this realistic material which plays a key role near the transition. And we can forget about all the others which are not relevant near the transition. So whether the couplings are relevant or irrelevant will be discussed when we talk about this RG. So based on this RG argument, we know that we better start from the simplest possible model or minimum model that we can manage to actually capture these key features near the phase transition, because oftentimes these results are model independent, and this universality clause offers as the justification that we could throw away all the other irrelevant degrees of freedom. So now let's take a second approach that we can construct the simplest possible minimum models that can describe the phase transition at finite temperature. And in a spin system, this well-known Ising model or Ising magnet provides a prototypical example of the minimum model requires to get this phase transitions for magnetic or spin systems. We will analyze the Ising model or Ising magnet first. So as I mentioned last time, suppose we try to describe a bunch of spins or magnetic moments for magnetic materials, and we can simplify the system by allowing the spins to point to either this plus or minus z direction and not along the other directions, although the spins could actually point to any directions in three-dimensional space. But suppose that there are a class of magnetic materials where the spins can only point to this plus or minus z, then they are called the Ising models. And there are two types of Ising model, the ferromagnetic type or anti-ferromagnetic type. We will discuss in more details in just a moment. So let me just define my Hamiltonian for an Ising model. Suppose this is the Ising ferromagnet where we have some nearest neighbor spin interactions, and this SI represents the spins on the lattice, and it takes a value only, say, along this plus or minus z direction. So it can be just in unit of h bar or half of h bar, just plus or minus 1. And therefore, it is just a coupling of the nearest neighbor spins, but all the spins can point to just plus or minus z axis. That's all. So it's the nearest neighbor spin-spin coupling, and this coupling constant for Ising ferromagnet is when there's a minus j, and j is actually positive. And this is very simple to understand why the ground state of such a Hamiltonian is the Ising ferromagnetic state. It is because when this temperature becomes 0, then to minimize free energy of this Ising system, and the obvious solution is that all spins are parallel to each other, so either pointing up or pointing down, because there's a minus sign here and j is positive. So when all the spins are pointing to the same direction, say a plus z direction, then this energy associated with that arrangement of the spins is minimized. And we know from statistical mechanics that whenever the system finds a minimized energy state, and that state should be the ground state or statistically favorable state. And therefore, this kind of all parallel configurations is actually a ground state or a ground state phase of this Ising model. All right? And this is a very simple and naive toy model, because we know that in realistic materials, say magnetic materials, the spins can actually point to any direction in space, right? So why do we just restrict ourselves to the Ising direction, right? This plus or minus z. But of course, there's a subclass of these magnetic materials which I just mentioned. Some interactions and isotropic coupling, such as spin-optic coupling and other couplings, which favors the situation that the nearest neighbor spins should be aligned to the same direction. But this is very simple and even naive. And the second point, this is a really simplest possible model, is that the spins can actually show some long-range interactions, not just restricted to the nearest neighbor. For example, the spins on the side I may actually interact with spins on any other side. So it can interact with the nearest neighbor, but of course this is just a highest probability processes. But the spin on side j can actually interact with all the next nearest neighbors and second, third neighbor, and so on. And it, of course, can actually couple to all the spins over the lattice, okay, over the long range distance. So such a long range interaction is really complicated to study. But the nearest neighbor coupling or shortest range couplings is actually the simplest case that we can imagine that we are able to analyze. So as we see later, that this Ising model, either ferro or antiferro, will show the very simple solutions in one dimension, and we know this critical behavior. So speaking of this critical properties, we know that for the Ising spin system, say the ferro case, this ground state is actually this fully polarized or fully parallel spin configurations, but we know that for temperature higher than critical temperature, all the spins becomes disordered or random orientation. Okay, such a disordered state is a high temperature state. So as we mentioned last time, or even earlier, that somewhere between the 0 temperature and finite temperature Tc, there should be a phase transition at T equals Tc. So we expect that this phase transitions would occur somewhere between 0 temperature or low temperature and high temperature regime. And for the simplest toy model like this Ising ferromagnet, we are able to analyze this phase transition both analytically and numerically. Okay? And we can extract those critical behaviors and those critical exponents, alpha, beta, gamma, delta, and so on, in a more precise way. So this is what we will do next. So let me just remind you this procedure that we analyze this simplest toy model, this Ising ferromagnet, and we follow the statistical mechanics, and we like to show from this partition function and the free energy of a finite size Ising model, and we try to make the system size go to infinity and see whether this phase transition can occur in principle. So let's just analyze this in a more statistical mechanical way. So we start from the minimum model, which is the Ising model, and we try to solve this model at the finite size, and we could also try to study the situation when the system size go to infinity, and we try to ask the question whether or not in principle this phase transition can occur, because we know from the earlier definition that the bulk free energy density should either have the first order jump or the second order jump in order to show this phase transition, and we will analyze more precisely whether this jump will show up. So let me just define my Hamiltonian of the Ising ferromagnet in the presence of the field, where this magnetic field acting on the side I is represented by this Hi here. So I intentionally put the minus sign in front, and we add this nearest neighbor spin-spin coupling, okay, where this Si and Hj is actually Ising spins, and I and J, this nearest neighbor sites. Okay, so this Hi times Si is actually Zeeman energy. For a local spin coupled to the magnetic field, we have the Zeeman energy minus Hi dot Si. Since both Hi and Si points to the Z or minus Z axis, here's the total Hamiltonian. Of course, we can have more terms than just these two terms, but again, to start from the minimum model, and these two terms are the most important terms in the minimum model, and we will calculate the partition function of free energy starting from this Hamiltonian, and we try to analyze whether or not in the thermodynamic limit or at any finite size, this free energy corresponding to the Ising model will show the signs of phase transition, meaning whether or not we have this jump or this continuity in the free energy density derivative relative to the coupling constant. So next time we will continue analyzing the partition function and the free energy of this Ising Hamiltonian, and we will clearly show that the phase transition can occur only in the thermodynamic limit. So from this partition function and from the free energy, and we show that phase transitions occur only in the thermodynamic limit. Okay, so at any given finite size, we cannot have a phase transitions based on the simple model calculations for the Ising ferromagnet. Okay, so that's our next job. So let's stop from here for today. Okay, so I'll see you next time.